Hi, and welcome to a new lesson from Easy Chemistry. This is Mr. Kusai, and today we're going to continue what we started in a previous video. We're studying about the electron configuration. Today we're going to focus on the rules and the principles. Our objective for today is to understand the main principles used in electron configuration. We have the keywords: electron configuration, Aufbau principle, Pauli exclusion principle, and the Hund's rule. In the previous video, we studied the principal energy levels and their sublevels. We studied that when n equals to 1, we have only one sublevel, and which is S. And when n equals to 2, we have two sublevels. When n equals to 3, we have three sublevels. And when n equals to 4, we have four sublevels. I recommend you guys, before you continue this video, to watch the previous video if you haven't watched it yet. So, the Aufbau principle, it states that each electron occupies the lowest energy orbital available. That means when we start the electron configuration, we always start from the lowest energy level or from the lowest energy orbital available. So, from the previous lesson, we studied this diagram for the principal levels and their sublevels, and we know that when n equals to 1, we have only S. But which S? Because n equals to 1, that means this S belongs to n equals to 1, so it's going to be 1S. And when n equals to 2, we have two sublevels, S and P, but because n equals to 2, that means we have 2S and 2P. And when n equals to 3, we have 3S, 3P, and 3D. When n equals to 4, we have 4S, 4P, 4D, and 4F. Now, what if we have n equals to 5? Also, we will have 5S, 5P, 5D, and 5F. We studied also that each sublevel, it has something called orbitals, and each orbital, the capacity is 2 electrons, or the maximum number that we can put in each orbital is 2 electrons. Now, in n equals to 1, we have only one S, and this one is the lowest energy. In the diagram, we will check. When n equals to 2, we have 2S and 2P. n equals to 3, we have 3S, 3P, and 3D. When n equals to 4, we have 4S, 4P, 4D, and 4F. Now, we have this diagram in terms of the energies and the sublevels. So, the energy is increasing from bottom to top, as you can see. Here we have the 1S with the lowest energy. Here we have the second S, it means 2S, and 2S has higher energy than 1S. So according to Aufbau principle, all the electrons, they occupy the lowest energy orbital available. So always we're going to start from 1S because it's the lowest energy level. And S, as you remember, it has only one orbital. As you can see, it's one orbital, and the capacity or the maximum number of electrons we can put is 2. So if you put 2 electrons here, now if you have the third electron, we're going to start with 2S because 2S is higher energy than 1S. What if we have 5 electrons, for example? So we're going to put 2 electrons in 1S and then 2 electrons in 2S, and then we still have 1 electron, we can put it in 2P. What if I have, let's say, 8 electrons? So 2 electrons in 1S, 2 electrons in 2S, that's 4. We still have 4 electrons, so I can put the 4 electrons in 2P. As you remember from the first video, we put them single, 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 and then we double them, but the opposite spin. That is 1, 2, 3, 4, 5, 6, 7, 8. Again, Hund's rule, it says that the electron should occupy the lowest energy available. All right. The second principle is called the Pauli exclusion principle, and it states that the maximum of two electrons can occupy a single orbital, one orbital, but only if the electrons have opposite spins. And when we say opposite spins, that's why we write the arrows one up and one down, because also the electrons they are spinning, or they are moving around the nucleus, but at the same time they are spinning like this. So one of the electrons will spin like this clockwise, and the other electron will spin anti-clockwise. That's the only way we can put the two electrons in a single orbital. This is the Pauli exclusion principle. So for example, in this diagram, what if we have 5 electrons? According to Aufbau principle, we need to start from the lowest energy orbital available, which is 1s, finish, 2s, finish, and then 2p, finish, and then 3s, finish, etc. So this is how we start distributing the electrons. So I have 5 electrons, so I'm going to put 2 electrons in 1s, but according to Pauli exclusion principle, I need to put 2 electrons the opposite spin, one up and then the other one should be down. Now I put 2, I still have 3 electrons, so I'm going to put 1 up, 1 down in 2s, leaving 1 electron left, so I'm going to put it in 2p. So the electron configuration now, 1s, it has 2 electrons, 2s, it has 2 electrons, and 2p, it has only 1 electron. What if I'm going to change the color, because I'm going to write, if I have, for example, 8 electrons. So we write already 2 and 2, 4, 5, then 6, 7, and 8. I cannot write in 2p, for example, and you will see in Hund's rule, I cannot write 2 electrons in p like this, and you will see why. So this is the correct electron configuration. So when I have 8 electrons, I'm going to write 1s, 2. That means in the main level, first principal level, we only have s, and in this s we have 2 electrons. Then in 2s, we have also 2 electrons. Then in 2p, we have 1, 2, 3, 4. So 4 electrons. And the total number of electrons are 2 plus 2 plus 4 is 8 electrons. All right. The third rule or principle, it's the Hund's rule. And it states that single electrons with the same spin, it means up, 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 must occupy each equal energy orbital before additional electrons with opposite spins, down, down, and down, can occupy the same orbitals. Let's check this image here. This is the correct way how we write the electron configurations. So for example, we have here all right, we have here px, py, and pz. That means this is the p orbital as we study it, and we have the p sublevel, and we have 3 orbitals for p, and we call it px, py, and pz for these 3 orbitals. How are they distributed? Single, 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 and single, and then we double them. So if I have 5 electrons, I'm going to write them 1, 2, 3, and then 4, 5. So it states that single electrons with the same spin, like those, must occupy each equal energy orbital, because those in P, these three orbitals, in terms of the energies, as you can see here, they are equal in the energy. This Px, Py, and Pz, they are equal in the same energy. They have the same energy. Before, the additional electrons with the opposite spins can occupy the same orbital. I think it's clear enough. Now we have valence electrons. What is meant by valence electrons? The valence electrons are located in the atom's outermost orbitals, and they determine an element chemical properties. You will see that when we study the periodic table and when we study the ionic compounds and the covalent compounds. So the valence electrons, they are the electrons in the outermost shell. That means, for example, for the chlorine atom, this is the inner shell, n equals to 1. This is n equals to 2, and here n equals to 3. The outermost shell for the chlorine is n equals to 3. We need to count the number of electrons in it. So the chlorine, it has 1, 2, 3, 4, 5, 6, and 7. That means it has 7 valence electrons. What about this atom, for example? Also, we have n equals to 1, n equals to 2, n equals to 3. So the outer shell level, we have only 1 electron. So the number of valence electrons, we have here 1 valence electrons. It's simple. The valence electrons are the electrons in the outermost shell orbital of the atom, and they determine the chemical properties. For example, this atom is a metal. We will check this when we study the periodic table. This atom here is a gas, and it's a halogen gas, and it has 7 valence electrons. So those valence electrons, they determine the chemical properties of the element. Last thing we're going to study in this video is the electron dot structure. We need to understand how we write the electron dot structure. It consists of the element symbol representing the nucleus and the inner level electrons. The inner level electrons, for example, for this atom are these in n equals to 1 and n equals to 2. And n equals to 3 is the outermost shell where the valence electrons are. So the electron dot structure, it consists of the element symbol, which represent the nucleus plus the inner level electrons, surrounded by dots. And those dots, they represent the valence electrons. As you can see, this is a section of the periodic table. For example, this is group number 1, and you see 1 dot. What does it mean? It means that the hydrogen, it has only 1 valence electron. Lithium, it has 1 valence electron, because lithium, from the periodic table, it has atomic number of 3. So we have 2 electrons in n equals to 1 and 1 electron in n equals to 2. So the outer shell electrons, yani the valence electrons, are 1. So if I'm going to write the Lewis structure or the electron dot structure for this element lithium, we need to write the element symbol, which is Li, and then we're going to write dots about how much we have valence electrons, and we have only 1 valence electron, so I'm going to write only 1 dot. Let's check, for example, the oxygen. Oxygen, from the periodic table, we have atomic number of 8. So the electron distribution among the principal levels is going to be the first orbital, we have 2 electrons, and the second orbital, we have 6 electrons. Don't forget, the maximum number of electrons in the second level is 8, so we can put all the 6. Now we have 6 electrons in the outermost shell. That means 6 valence electrons, and we write the electron dot structure for the oxygen, which is oxygen and 6 dots, as you can see for the oxygen. Now, example problem. Write the electron dot structure for carbon atom, and the carbon C, it has 6 electrons. The atomic number of carbon is 6. So I'm going to write 2 and 4, that's 6. I have 4 valence electrons. So I'm going to write the carbon symbol and then 1, 2, 3, 4 valence electrons. As you can see it's right here. What about the fluorine atom? Fluorine atom F, from the periodic table, the atomic number is 9. That means we have 2 and 7, meaning we have 7 valence electrons, and the fluorine dot structure is going to be 1, 2, 3, 4, 5, 6, and 7 valence electrons. I want you guys to practice about, let's say, C, which is the nitrogen, which has 7 atomic number, and D about the aluminum Al with 13 electrons. I hope you guys learned something new today. Please keep tuned. We're going to have some examples next lesson about the electron configuration for the elements, and also we're going to have some exceptions about the predicted configuration. I hope you guys learned something new today. If you have any question, just write it in the comments. I will read all the comments and I will answer all your questions. Have a nice day.